Deodar's decomposition is to study the Cousin-Lussig R polynomial, or really Cousin-Lussig polynomials. So the Cousin-Lussig R polynomial can be defined as the finite field point count of a Richardson cell or open Richardson variety, and they are the pieces that's used to construct the Cousin-Lussig polynomial. So to understand these R polynomials, Deodar introduced a decomposition of the open Richardson variety into pieces that are isomorphic, that are of the form, C to the A cross C star to the B. And so we can then express this finite field point count as summation over all these pieces, Q to the A times Q minus 1 to the B. Okay, and these pieces are labeled by something called distinguished subword. So if we fix a reduced word of V, whatever reduced word that is, a distinguished subword is one where where we sequentially decide if each of the SI, if we want to include each of the SIs. If including that SI will decrease the length of the product that we have so far, then we have to use it. That's the red SIK. And if not, so if the length will increase, we can choose to use it or not. So as an example, if we set V to be the permutation 3 to 1, and we take the reduced word S1, S2, S1, there will be two distinguished subword for U being the identity. So I can choose, I can simply not choose any of the simple reflections. So U could be 1, 1, 1. Or so if I say I choose the first S1, I do not choose the second S2. And now when looking at the third, the last S1, we see that if we multiply it, the length will go down, and we'll have to include it. And this is the red S1 towards the end. And these two are the two distinguished subword for you. And so the Richardson cell can be decomposed into the Deodar cell, where we're taking the strong union over the distinguished subwords, and each Deodar cell will be isomorphic to C star to the number of ones, over distinguished subword cross C to the number of red SIs. And we even have a explicit parameterization using all these C stars and Cs of the Deodar cell. We can think of them really as a product of some very simple matrices. So again, we use the example, the S1, S2, S1 example. So here we have two distinguished subwords, and the first one has 3 ones, so the first piece will be isomorphic to C star to the cubed. And the second one has a 1 and a red S1, so it's isomorphic to C star cross C. And we can actually...
Just sorry to interrupt. What is the difference between Deodar-Haas result and Maas reached?
Right. So I think Marsh and Reach give this explicit parameterization in terms of these product matrices.
Yeah, but it looks a lot like Deodar-Haas, but maybe there's a difference.
So in their case, they're also thinking about the totally non-negative part of the Richardson cells, and we'll see later that all of them actually lies in a single Dildar cell.
You just
So I figured,
this theorem you're stating, it looked like
ah,
the Haas result from 85. So
yeah. So I should probably only mention Dildars
okay,
in
okay, thanks.
the parentheses. Yeah, that's right. Yeah, thank you. All right. Yeah. Um, so one can explicitly parameterize the Dildar cell by taking products uh, of matrices. Really, it's we have some two by two small matrices that we embed inside this three by three larger matrix. Here, this is the two by two matrix 10p11, 10p21, and 10p31. We take the product. And similarly, similar for the other case. Okay, so um, yeah, so for us, we generalized Dildor's decomposition to our into our tilted setting. So if we fix a what we call the tilted reduced word, I won't tell you the precise definition. It's a little bit complicated and there's too much details involved. Um, we define the notion of tilted distinguished subword, where it's still the case that at each Sij we're deciding or Sik we're deciding if we want to uh, choose this simple reflection or not. But then there are some rules where we have three different colors for when we choose the SI case. Um, as an example, so for V permutation 246513, we have this tilted reduced word, whatever that means. And there are four tilted distinguished subwords for the permutation U equals 512, 3, 4, 6. And what we proved is that the open tilted, the tilted Richardson cell can be decomposed into, again, small pieces, each piece labeled by a tilted distinguished subword. And each piece would be, again, isomorphic to C star to some power plus C to some power. And yeah, and in fact, if U is less than or equals to V in Strong-Brougham order, the tilted reduced word are just your regular reduced word, and tilted distinguished subwords are just your distinguished subwords. Yeah, and okay, so what can we do with this tilted generalization of Dildar decomposition? Well, first of all, as I hinted earlier, we can prove irreducibility of PUV. So for any tilted reduced word V that we choose, there's a unique distinguished subword that doesn't use SIK, the red SIK. And the corresponding tilted Dildar cell will be the unique cell of maximal dimension. Remember um, the yeah, so it will be a cell of the form C star to some to the power of LUV, where LUV is the really the dimension of our tilted Richardson variety, or in other words, the length of the shortest path from U to V in the quantum Brougham. And all the other cells will have dimension at least one less. And so yeah, so from there we know that TUV is irreducible, and this specific tilted deodar cell will be dense inside the tilted Richardson variety. Okay, so that's application one. Application two, this is total positivity. So a very old theorem by Bioner states that if a pole set is thin and EL shellable, then the pole set itself is the phase pole set of some regular CW complex. And it is proved by Brentifomin Postnikov that the tilted Bruhat interval, every tilted Bruhat interval, is thin and EL shallow. So the motivating question for us is that can one find a natural realization of such CW complex? And the problem here really has a rich history. So back in '84, Bioner showed that all Bruhat intervals are phase pole set of some regular CW complex. He constructed these regular CW complexes by inductively, recursively gluing a bunch of all the pieces together. This is what they call syntactically constructed. So Fomin and Shapiro, back in 2000, gave a conjectural description of a natural geometric realization of the CW complex using using the notion of total positivity. And the Fomin-Shapiro conjecture was proved by Patricia Hirsch back in 2014. So in 2007, Lauren Williams generalized the conjecture to the interval pole sets of any Bruhat interval. So now, instead of looking at a Bruhat interval as a pole set, and think of it as the phase pole set of some CW complex, we consider the pole set of all Bruhat intervals where the partial order is given by containment. So now we have a pole set whose elements are these Bruhat intervals, and order given by order given by containment. And so here you have to throw in a zero, which is smallest as the smallest element. And she conjectured that if we look at the Richardson variety and we intersect that with the totally non-negative part of the flag variety, it has a decomposition into a bunch of these smaller pieces where each piece is labeled by a subinterval of UV. So the conjecture is that this is a geometric realization of the regular CW complex that is this is a realization of the regular CW complex. And building on work of Rich and Williams, Gaussian, Karp, and Lam proved this conjecture. So for us, we've mentioned all these nice properties that Richardson variety has, and we are able to generalize them to tilted Richardson varieties. Why not think about why not try to generalize one more? Okay, so to do that, well, now we have all these rotations going on. We doesn't quite make sense to intersect tilted Richardson with just the totally non-negative part of the flag variety. So we modify the definition just a little bit. So if we fix the sequence A1 through n minus 1, we define the tilted totally non-negative flag variety, TNN A, to be the set of all flags such that the Fokker coordinate delta I1 through IK is non-negative, where here we ask that I1 is less than IQ, less than all the way to IK under this rotated order AK. So we think of AK as the smallest and AK minus 1 as the largest. So for example, if let's say A is sequence 432, then the flags in this tilted totally non-negative flag variety, well, we will have delta 1, delta 2, delta 3, delta 4, all non-negative. And we'll have, so for two element sets, now we're thinking of 3 as the smallest. So the non-negative Plukers are delta 3, 4, 3, 1, 3, 2, 4, 1, 4, 2, and then 1, 2. So if we just take, let's say, the determinant of the 2 by 2 matrix with row index 2 and 3, that's negative delta 3, 2. And similarly for the 3-element subsets. Now we can define what the totally non-negative part of tilted Richardson. So it's just the intersection of the tilted Richardson cell or tilted Richardson variety with this tilted totally non-negative part of flag variety. And it is yeah, and so here we actually know that the intersection of the so the intersection of tilted Richardson cell with this Tn and A will all live inside one tilted Deodar cell, and we have a explicit parameterization of this. And so we conjecture that this intersection will give us a regular CW complex, just like in the Richardson case proved by Gaussian carpet net.
What does regular mean again?
This is about the attaching maps are homeomorphisms. This is adjective to the CW complex. It's about how you glue the pieces together.
Okay, thanks.
Application 3, or really this is more of a conjecture. So we can define this tilted generalization of R polynomials as point counts of the open tilted Richardson cells. So there's this long-lasting conjecture combinatorial invariance problem that says that conjecture the R polynomial depends only on the poset structure of the Strong-Bourhau interval. And we conjecture that the tilted R polynomial, so the point count of tilted Richardson cells, also only depends on the poset structure of tilted Bourhau interval. Well, I seem to have 2 minutes, so let me just say a little more about this. But there's a way to think of the R polynomial as in terms of knots and taking trace in the Hecke algebra. So I think you take any reduced word of U, you take any reduced word of V, and you do something like Tu times Tv inverse inside the Hecke algebra, and you take the trace that gives you the R polynomial. We proved a tilted generalization of that, where you take a tilted reduced word of U, take a tilted reduced word of V, you still do TU, TV inverse, you take the trace, that gives you the tilted R polynomial to the point count in this case. And there are some more recent papers by Kalashin and Lam studying that the relation with between really comogery of open Richardson cells and they connected to some knot invariants, and so there are definitely also um, uh, things we can do in that direction. And thank you all for listening. I'll stop here.
Thank you very much. Thank you for the beautiful talk.